In this second Proteus 8.10 tutorial, we will look again at the automatic nightlight circuit. In the first example, I used a simple transistor switch to achieve the desired operation, which enabled me to demonstrate the basic features of Proteus which are involved in capturing a circuit schematic and laying out a PCB. In this tutorial, we will do the same again, but using a more complex circuit, which will also introduce some new components. This time I will use a comparator module to turn the LED on and off when the LDR voltage rises above or below a set threshold. Enter the schematic capture window using the button at the top. First, we import the necessary components by going to the Parts Manager, opening the search box, search for the desired part, and double-click to add to the active parts list. As before, the circuit consists of an LED, an LDR, and some resistors. In this case, however, we will also include a basic operational amplifier, or op-amp. I'm going to use the MCP602, which is a single-rail general-purpose operational amplifier from Microchip. An op-amp has 5 pins: the positive and negative supply pins, an output pin, and 2 input pins. The plus pin is the non-inverting input, and the minus pin is the inverting input. They are named such because if the op-amp is operating as an amplifier, then injecting an input signal into the non-inverting input will produce an output in phase with that signal, while injecting a signal into the inverting input will produce an output which is inverse to the input signal. A comparator is basically an operational amplifier with no feedback. The open loop gain of an op-amp is very large, somewhere in the region of 100,000, meaning that the output voltage will be the difference between the input terminals multiplied by 100,000. If the difference between the input terminals is 1 mV, then the amplifier will attempt to drive the output to 100 volts. If the difference between the input terminals is minus 1 mV, then the amplifier will attempt to drive the output to minus 100 volts. The output is sourced from the power supply rails, which in this case will be 5 volts. This means the output cannot become less than 0 volts or higher than 5 volts. This will have the effect that the output will saturate to 5 volts if V+ is greater than V-, or it will saturate to 0 volts if V+ is less than V-. This transition will be so fast it can be considered instant for this application. Based on this operation, we can assemble the circuit as shown. Remember that the LDR resistance increases as the ambient light level decreases. Again, it forms a potential divider with a fixed resistor, so the node voltage will rise as the light level falls. We will connect this node to the non-inverting input and use a second potential divider to apply a static voltage to the inverting input. The amplifier needs power to function, so connect the positive and negative supply pins to the power and ground rails respectively. The LED can then be attached to the output with a simple current limiting resistor. DC voltmeters and ammeters are available in the Instruments section. For debugging purposes, I can attach a DC voltmeter to both inputs to observe how the voltage changes when the light level is adjusted. I will also attach one to the output to see how the voltage behaves. Simulate the circuit by pressing the play button at the bottom left. The meters will now display values. Initially, the light level is high and the LDR resistance is low, which results in a low node voltage. The non-inverting input voltage is less than the inverting input voltage, and so the output saturates low. When the light level falls, the LDR resistance increases and the non-inverting input voltage rises. When the non-inverting input voltage becomes higher than the inverting input voltage, the output instantly switches from 0 to 5 volts, and the LED switches on. Bringing the light level back up causes the LDR resistance to decrease and the non-inverting input voltage falls. When it becomes lower than the inverting input voltage, the output immediately switches to 0 and the LED goes off. The amplifier has a limit to the amount of current it can source, which can range from just a few milliamps to a few tens of milliamps. If the LED requires more than this, then the amplifier cannot supply it directly. In such a case, the transistor from the previous circuit can be reintroduced as shown. The transistor behaves like a switch, allowing a small current on the base to control a much higher current through the collector. In the second half, we will look at the PCB layout, including the package and pin identification for the op-amp chip.